I introduce Dr. Swartz very briefly. Kenny received his PhD in mechanical engineering from the University of Illinois at Urbana-Champaign in 2021, specializing in the design optimization of macro-architected material. Upon completion of graduate school, he joined the computational engineering division as a computational optimization engineer in Lawrence Livermore. His current research includes topology optimization, shape optimization, and design for additive manufacturing. He is closely involved with the development of the Livermore design optimization software library, LIDO. So with this, I will stop the sharing my screen, and Kenny, you can go ahead and present your talk.
All right, so let's talk about design optimization for mechanical logic gates. So I believe I'll have plenty of time to get through the slides. So if anybody has questions, I encourage you to just take yourself off mute and interrupt me. I'm happy to answer anything that's confusing as we go. So first of all, what am I talking about? So mechanical computers are mechanisms that use components such as gears and levers rather than electrical signals to perform calculations. And these were once quite popular, and there's some cool applications. One of my favorite is actually the Norden bomb sight that was used in World War II to perform these mechanical calculations that were used to, automatically guide bombs at their target. But by the 1970s, these were largely replaced by electronic computers for obvious reasons, like much more efficient, much smaller. But there's been some renewed interest lately, and one example of that would be NASA's automation rover for extreme environments. And this was a project that was put out where the idea was to design a computer that could operate in extreme conditions where electricity wouldn't necessarily work. So for example, if you wanted to power a rover on Venus where it has an extremely high temperature and extremely high pressure, maybe acid rain, this would be problematic for electronic components, but you could conceivably develop a mechanical computing system to perform your operations that would be much more robust. So the ultimate goal here is we want to use topology optimization to design these digital mechanical computers. So what exactly do I mean by digital mechanical? So when we think digital, think binary, so like zeros and ones. And so generally in electrical computing, that's done by whether there's a electronic signal or not. But in mechanical, we're going to deal with things like displacements, which are more continuous. But what we want is mechanisms that like clearly snap between two locations so that we can measure this mechanical response, but in a digital way. So some of the requirements are going to be that there's no electrical power required to run these systems. They have no electromagnetic signature and can therefore operate in extreme environments. And while there's going to be some challenges here, there are benefits such as these things cannot be like, you can't say limit their performance by just restricting the electronic signatures, and they can hold memory for long periods of time without batteries. And so what we want to look at is there are some existing designs that were mostly developed by the manufacturing team here. And so we want to look at these and say, can we make these designs better? And what do we mean by that is maybe they're simpler, more robust to high stresses, more reliable. A lot of times these things, they come up with some complicated design that does work, but maybe it only works a few times, and we want to extend that life by lowering the overall stress. And right now we're kind of at the stage of just designing logic gates, and we'll get into what I mean by that shortly. But we also want to look at designing entire computing systems, and so not only just one gate that takes inputs and does some logic on them, but how do we best put these together in a sequence so that we can do more complicated things, such as like adding numbers together, and we want to be able to propagate that signal. That's a much harder problem. So I'm gonna use a pretty standard topology optimization formulation here. I think most people probably have seen a lot of these things. We have design variables that range from 0 and 1. These are our pseudo densities. Use a PDE filter to impose a length scale on the design, and then threshold that field. So it's kind of the so-called 3-field approach. I'm using a ramp penalization to help designs go to 0, 1, although that's a bit of a challenge in this work. And then we're going to look at, limiting volume fraction as kind of a standard thing as a constraint. And then we'll get into the kind of performance-based constraints and objectives just in a slide or two. One thing I wanted to point out is I am using the Livermore design optimization code, which is a graph-based framework for posing these optimization problems. So on the right there is an image showing this exact design problem where basically every operation you do becomes a vertex on this graph, and you just have to define the inputs and the outputs and the mapping between them. And then you also define the backward sensitivity, or if given some downstream derivative, how do you map that to an upstream derivative? And by defining the forward and backward description for each of these operators, we can pose this optimization problem and then use the graph structure to automate the chain rule to get our entire design sensitivities. And this is a really powerful way of implementing this type of work because it makes it very, very easy to change out objectives, constraints, like put additional features onto the problem and not have to think through the whole sensitivity analysis and how that's all affected. The graph handles a lot of that automation for you. And so basically the outlined portion of that graph is showing what I'd consider the parameterization part of the design problem. And so that's what's highlighted here on this slide. And then we'll get into the bottom of it is more of the actual elasticity problems that we're solving. So many of the things you saw on the last slide, I would consider kind of standard topology optimization formulations that you see in a lot of different literature works. There are two things that make this problem particularly hard that I wanted to highlight. So the first is that we have to have a nonlinear material model. We want to look at, motion such as like rotations and potential bucklings, and we need to form these mechanisms to perform complex logic. We really need to capture the nonlinearities. A simple linear model that misses all that rotation isn't going to work for us. But as we know, when we bring in a nonlinear material model such as Neo-Hookean, the void elements can create quite a headache, and we get a lot of numerical problems when they start tangling. And so I am employing here a technique that I found in the literature. The basic idea is that you use a linear material model for your void elements, but you use your nonlinear Neo-Hookean material in the solid elements, and you have this way of interpolating between the two, where specifically you weight the displacement gradient by your density field. And what that does is in the void elements, if you get tangling, because you're weighting by that density, which is near zero, it cuts down the displacement gradient that the material model sees, and you avoid all those numerical issues. And so it's quite a nice way of handling this, and it's worked really well for us. And then the second challenge, which comes into this problem, is the fact that we have bistable mechanisms. So we think about these gates, and as I mentioned in the beginning, we're talking about digital mechanical behavior. So we're going to have inputs where we have basically a displacement that comes from some external object that goes between two distinct states. And we're going to model that through a bistable spring that's relatively stiffer than our gate is. And so the input is going to either be snapped into its off or its on position. And so we model that with this fourth order energy curve, which gives us a cubic force displacement. And so when we push on this thing, it'll give us some resistance up to a point, and then it'll kind of snap through to its second configuration. And this can create a number of issues in the optimization. The first one is that the simulations are very hard to converge. And so if you use just a classic Newton's method, you're almost never going to get these things to converge reliably. A line search might help, but we've had to use a much more robust solver, which is it's a trust region based solver. That the key part of it, though, is that it minimizes the energy of the problem rather than just the residual, which is done in a standard Newton's method approach. And this has allowed us to converge these simulations very reliably, because for design optimization, every iteration has to work. If the simulation crashes somewhere in the middle, you kind of lose out on everything. And so to give you an example of types of problems that this solver can handle, here shown on the right. The top right, you can kind of think of maybe like a soda can that's being crumpled. This is a very hard problem for most solvers to handle, because you have these thin walls and it crumples up and buckles in a complicated way. And then the bottom right one is actually very relevant here, because this is the bistable mechanism that's going to supply the inputs to our logic gates. So you can see how this thing slides. Because there's a preload put on this to create compression, there's two stable equilibriums where this beam is sitting to the left or to the right where it wants to settle into. And so you can imagine if you push on this a little bit, it'll provide some resistance, and at some point it snaps through. And handling that both in the solver and then in the effect that has on the design optimization is one of the main challenges here. So let's talk about how I am framing the optimization problem to overcome this. So what I'm going to do here is I'm going to have one design that is going to we're going to look at a number of load cases operating on that same design. And these load cases, so there's going to be 3 of them. So in the first one, we're going to apply a prescribed displacement in the top left. Here, I call this gamma 1. We're going to apply a displacement down. And then we're going to have these bistable springs at gamma 2, which is our second input location, and at gamma 3, which is the output. So that's going to be one load case. And then there's going to be another one where we push up from this gamma 2 location. And then there's going to be a load case where we apply both of those loads simultaneously. And then the idea is that by choosing what we want this output to do for each of these load cases, that will dictate the type of logic that our gate is able to handle. And so, again, what do these 1s and 0s mean? Well, it's because of the bistable mechanisms here that are again, relatively stiff compared to the Young's modulus of the material. They will sit in basically 2 energy wells that give us this very distinct binary signal. And so what we're going to do is we're going to apply these loads, and from these 3 load cases, we'll write a series of constraints and then come up with an objective that will drive us to the type of logic table that we want our gate to perform. And so the ones that are always true is that when you actuate input 1, you don't want input 2 to move. That's just kind of the definition of this load case. Same thing with 2. When you apply this displacement, you don't want input 1 to move. And then the key thing is looking at what you want the output to do. And what I found is that if you start with a very low density initial guess for your design, any output that you want to stay in its off position, you can write a constraint, because initially that will be in the feasible region. Because when you apply this displacement, if this is pretty weak, almost air material, it won't affect the output. And so since we started in its off position, you can write a constraint that says it must stay in its off position. The harder part is when you want to actually flip an output to its on position. So now you have to overcome, kind of going through that energy barrier. That has to go into the objective. And so the objective is basically that you push kind of as far as possible in the direction of that second energy well. And that does a couple things. Is that it makes you set up all the constraints so that the problem starts feasible, and then in that way can always stay feasible. And the optimizers tend to perform better in that environment. But then also, we're going to go through a discontinuity in the gradient when we snap through to that second energy well. And so if we were to actually take our design sensitivity right at that snap point, the gradients wouldn't be very meaningful. But the hope is that it's a small part of design space that we can kind of go past. And then if we push away from it, hopefully we can converge kind of in a smooth region of our design space. And so all of these load cases, in terms of how this is set up in our Lido graph, would just be this bottom region here, where we have 3 different load cases, and then all of our derived QOIs that formulate our kind of performance-based constraints and objective. So if we set all this up right, sorry, I'll skip through the animations I didn't use. We are able to get some cool looking gates out of this. And so this is the design conversions for a couple different gates that I'll show you more specifically on the next slide how they function. But we are getting pretty good black and white designs. And this is in the presence of these bistable mechanisms that can create quite a headache if you don't handle them properly. All right, so what are these gates doing? So we looked at 5 different logic tables that we want to be able to realize with these designs. So the first would be an AND gate. So what does that mean? If either of the inputs are actuated on their own, the output doesn't move. But only when they're both actuated, then we see the output flip to its second position. And here I've annotated what I mean by these 2 positions. You can see it really does snap through very distinctly, where it's sitting at the 0 and then it snaps over to its 1 state. And so the difference between the rows here is just looking at how we handle the lateral part of the inputs. So basically, are we actuating it kind of think like railroad tracks here on the bottom, where we're enforcing that the displacement's only vertical, or are we allowing them to slide a little bit laterally? I'm not sure which of these is the better model. We're still working on building these and seeing how they really perform, but just wanted to point out the difference between these designs. All right, so that's the AND gate, where we look at basically moving from a 0 state to a 1 state, which we define as going from left to right. We're calling the NAND gate, where we start on the 0 state, is kind of on the right energy well, and then we want to snap through to the left. And this is a little bit more challenging because we have to, it's kind of like a force inverter, if you've seen those in compliant mechanism design. So yeah, you'll see here how if either input is actuated, nothing really happens, but only when they both are, we do get that snapping mechanism. The OR gate is probably the easiest one to get to work. So basically, you want the output to move when either input is actuated or when they both are. So this isn't too hard to figure out. You could probably design this one on your own based on intuition. But the NOR is harder because now it's similar to the OR, but flipping that actuation direction around is quite a bit more challenging. And I think my favorite gate is the XOR. So this is the exclusive OR. So what we mean here is that we want to actuate if either input is flipped to its on position, but when they both are, we actually want to undo that and make sure that the output is not actuated. And so I think the way that it does this is quite clever in that there's basically this middle region that really stretches out only when both inputs are actuated. It's a little bit maybe more clear at the bottom here. So if one flips it over, two flips it over, but then they both go, and it actually just opens up this middle and avoids pushing the output to the right. So this is a gate that at least I would not have been able to come up with a mechanism. I wouldn't have been able to design this one on my own in a way that worked. I think it's cool that the optimization could find this solution. And so one thing I want to point out as well is that I am using top-bottom symmetry here, so that the parameterization region is just really the top, and then that is mirrored over a symmetry plane. And in that case, I lied to you a little bit because I said there were 3 load cases. You really, with symmetry, you only have to consider 2, since applying your displacement to the first input for a symmetric design, and we'll do the same thing as if you just applied it to the bottom. So there's really just the single input and the both input load cases. We just found that the designs generally came out better if they were symmetric, but due to some instabilities, that they didn't always give you symmetric designs at the end. So the designs converged better, and we got much better results if we just applied that top bottom symmetry by construction. So what I want to show here is that you can converge to different local minima for different start points. So the columns are different volume fraction limits, and the rows are different start points. And so there are definitely some repeated local minimum, which is good. So it's not like you get a different design for every random start. But in trying to find some of the harder logic, it does make sense to start from a few different random generations of pseudo density and then kind of see where the design goes, because some of these maybe satisfy the logic and other ones may not be able to. These are the NOR gates, just showing you that for I think it's true for all the different logic types that you would converge to different local minimum, but there are some consistent trends throughout the different logic. All right, so I think one takeaway we have is that we can definitely use optimization at this point to come up with simpler mechanisms for these mechanical logic gates. So in the top, these are animations of some human design gates that our manufacturing team came up with. And these definitely work. They do satisfy the logic, but there are a lot of different pieces. I think it took quite a bit of tuning to get these to work how they wanted. And you can see there are these very small features and sharp corners, which make these designs less robust to cracking over repeated use case due to high stress. And with topology optimization, we can achieve the same logic, but with, I think, much simpler mechanisms. And we haven't done it with this work, but we could definitely look at minimizing the stress. We can do that either from topology optimization, although that brings in a certain set of headaches. We want to look at taking these topology optimized designs and conformally meshing them and then doing shape optimization to further refine them. And so one of the next steps we want to do in this work is to take these designs and actually print them and make sure that in real life, they operate as we're predicting with our models. And so one of the first things I looked at was looking at the true 3D behavior. So everything I showed you up to this point was modeled with a 2D mesh, and so we can completely ignore out-of-plane effects. And so one of the things I wanted to look at was varying the third dimension. So what I'll do here is the design will still be 2D, but it's kind of 2.5D in the sense that we'll take that 2D cross-section and then extrude it into the third direction. And then in addition to looking at that finite thickness effect, I also, as a validation step, took the 0.5 ISO surface of these topology optimized designs and then fit a conformal mesh that was slightly smooth that captures the topology. But now we can model it with a conformal mesh that hopefully will be more accurate and gives a better idea of how these things will perform in real life. So you can see here, this is one of the same designs you saw earlier, but now just with that conformal mesh. And this one still does satisfy the logic we were hoping, which is a good sign. And then one of the other things we're looking at is to actually print these, is how we would, in our computer model, it's easy enough to say, here's an essential boundary condition where the displacement's 0, but in real life, we can't make these things perfectly rigid. We have to actually fix it to some like whether that's gluing it to something or hooking it up to some grounded support system. So we want to actually model that support system. And so here we were looking at just these pyramids where they could be glued onto some substrate below. And then this would provide a not exactly rigid connection, but it would still be an anchoring point that would be much more rigid. And so when I started looking at these, so now we're taking in all of these effects. So we've gone from just a strictly 2D topology optimization with these gray, blurry boundaries. We fit the conformal mesh. We've added a thickness and these realistic supports. And then, of course, things didn't work as I was hoping. And the first issue I realized is that the structures were modeled as very thin. And we immediately saw out-of-plane buckling that was hidden both in the initial 3D simulations, because I was using symmetry in the kind of out-of-plane direction, but also in the 2D simulations, we obviously have no hope of getting the out-of-plane motion since it doesn't exist. And what I found is that we can get kind of different modes of that buckling, but even if the inputs are held fixed in the Z direction or that out-of-plane, the structures were actually just too weak to support the loads that they were taking on. And so that was one thing we had to look at, was how do we overcome this out of plane motion that's completely killing the performance that we'd be predicting from our 2D code. So yeah, you can see these are just not behaving at all how we were hoping. And so the first thing to do is to go back and put that third dimension in the topology optimization. And so this is where, as I mentioned earlier, the design is strictly 2D, but we're mapping it onto a 3D mesh. And then now we're actually doing the performance calculation inside the optimization loop in a 3D mesh, so we can capture this out of plane. And we can see that by one of the simplest things is to just increase the thickness of the structure, just as kind of a proof of concept that we can fix this in the topology optimization. So if we just make it thicker, that is one way to stop it from buckling out of plane, to give it that more lateral stiffness. And here I looked at just for different thicknesses, does it change the design? And mostly I'd say the answer is no. And so this kind of tells us what's the minimum thickness we can get away with without buckling. For this case, it was about a third of the domain size. So as I mentioned, one of the things we want to look at is going to shape optimization on the conformal mesh. So we're not quite there at the moment, but the ultimate goal is to use topology optimization just to create an initial mesh that we can perform shape opt on. But with this, one thing we'll have to be very careful about is avoiding self-contact, because we would either have to model that contact in the prediction of the performance, or we can just write design constraints to avoid it, which would probably be the easier way to start, because this was just kind of a sample I ran where you can see that the optimization gave me this shape, but the structure started intersecting with itself. But since there's no contact in the model, it doesn't see that. So it makes an unrealistic structure. But we think we have a handle on how we can implement these constraints to avoid this type of contact. And then we hope to use this technique to make these gates actually work a lot better. So to wrap up, we are developing a framework for topology optimization of these general mechanical logic gates. And one of the key things we realized early on is that modeling the nonlinearities is essential to capture the relevant kinematics. You need to capture things like rotations and large strain effects to get any sort of complex logic. And so this brings in some challenges that the nonlinear solver must be very robust. It can't really fail ever. And then we needed to use that material model interpolation to avoid numerical failures for large strains in the void phase. And then we found that the presence of these bistable mechanisms leads to significant discontinuities in the gradient. And you could kind of get into situations where your objective and constraints just oscillate wildly back and forth between the two states. And so we have to figure out how to formulate the problem in the presence of these to kind of pushed ourselves away from the discontinuities and to be able to converge our designs. Unfortunately, I don't have any of the latest and greatest work on this that made it into the slides before they had to be reviewed. But I will say that we are looking at ways to basically rewrite those spring models to make it so that we can capture the kind of the realisticness that we need to make sure the mechanisms would perform how we want, but trying to smooth out some of that bistable behavior so that our gradients are smooth everywhere in the design space. And we're finding that that actually works a lot better. So hopefully we'll have a publication out on that in the near future. But with this work, we have designed 5 different types of logic gates. So that's the and the or, and then different variants where we're changing the direction. So like a NAND, for example. And then we're looking at further improving these with shape optimization, where we'll have to figure out how to avoid the self-contact, but then we'll have a much better prediction of stress that we can mitigate. And then eventually the idea is to, once we can reliably compute these gates how we want, look at ways of how we can you can think of it as like a multi-scale optimization to combine many gates to design more complicated computing systems. And so with that, I think there are plenty of time for questions.
So thank you very much, Kenny. Very interesting talk, and I enjoyed your presentation. Thank you. We have a series of questions in the chat, and I also encourage our audience, if you have any question, you can unmute yourself or raise your hand and ask the question, or type it in the chat, and I will try to read it for Kenny and get the answer. So I will start with the chat because we have a series of questions here. So first question is from Narayan Alaru. Dr. Alaru asking, how can they move with no power? I think he's referring to your mechanical logic gate. And are you exploring noise to get the power?
So when you say no power, are you referring to my comment on the
yes.
No electrical power?
So, and please, Professor Adaru, you can unmute yourself and ask directly from Kenny if I'm not very clear about this.
Yeah, thank you. Thank you, Kenny, for a nice talk, and thank you, Ahmad. Yeah, so I was referring to this particular slide where you said the ultimate goal is no electrical power required, and I'm not sure how you can actuate with no energy supplied.
So it's not necessarily no energy, it's just no electrical power.
Okay, and how would you do that?
So that could be just something pushing on an input. It can be, think of like gears or levers.
So this would again be some mechanical pushing, or?
Yeah, that's an example. So
again, you have to do some work on that, right? I mean,
yeah, but that doesn't mean you have to have a battery.
Okay, I see what you're saying. Yeah. So what's the response time of these gates? I mean, how long do they take to respond?
So we're modeling them as quasi-static, in the sense, like, I don't think we're going to be operating in the dynamics regime where you're looking at like we just want that in its stable configuration when the inputs are actuated, that we know if input 1 is at state 1 and input 2 is at state 0, then we know the output goes to a particular state. That's kind of the level we're operating at now. We're not actually looking at like the dynamic effects of like how long it takes the signal to propagate. I think to do larger computing systems, we would eventually have to make sure that the dynamics isn't killing the propagation, in some way that we don't want it to. But right now we're just looking at quasi-static models of just, it kind of in its resting state is all the logic satisfied. Does that answer your question?
Yeah. Thank you, Kenny.
Thank you, Narayan. So next question is from Shamu Duta. He's asking, computationally, how expensive it is to obtain the optimized design for these logic gates?
Yeah, so that's a good question. Let's see. So generally, I am taking so for the results you saw here, I was taking a 2D mesh that was 100 by 100 elements. And then I had to do, for every design iteration, I had to do these 3 load cases, which I would generally break up into a series of prescribed displacement load steps. And so the amount of time per iteration does depend a lot on what's going on inside the structure. If you're getting a nearly linear response, it might only be 2 or 3 linear solves to get you there. If something in the internals start buckling, that can really go up. And so let's see, I can only really give you rough estimates. I don't have the numbers written down here, but I would say I was running on a computing node that had 112 processors, and generally I can get a design in under an hour.
So whole optimization iteration, not one iteration. You are talking about
right. The entire design of one gate would be on the order of an hour.
Okay, for this size. So
for 100 by 100 mesh with
Okay. Now that we are talking about the mesh, did you check if you go finer or coarser mesh, what will be your solution? Will you see a different layout for your gates?
Yeah, I mean, I think it's the answer to that would be really similar to kind of the answer you would give for any sort of like cantilever, right? So if the feature size is imposed by the PDE filter. And so if you refine your mesh and then you make your filter radius smaller, you will get more intricate features for sure. If you keep the filter the same and refine the mesh, it should converge to a consistent solution because you're taking the mesh dependency out via the filter. For some of the gates, if your filter is too big, it will just never satisfy the logic, right? Like you can't have a beam that's a third of your domain size and try to do anything interesting with like flipping the direction of the inputs. So there's kind of like a required resolution to get, the kinematics to be complex enough to satisfy the logic. And then if you keep refining beyond that, you will definitely get more complicated features in the same way you would if you kind of with any topology optimization, if you allow your design space to keep allowing those smaller features.
Okay, so thank you. Next question from the chat is, thanks for the presentation. It says, what would be the major difference with TOPO, I think topology? TOPO, what is stand for TOPO? I don't know, but for compliant mechanism. What would be the major difference with TOPO for compliant mechanisms? If I'm not clear, you can unmute yourself and ask your question.
Yeah, actually, I'm just asking, what's the difference between topology optimization for compliant mechanism? Yeah.
So in the sense of like how do the designs differ from compliant mechanisms?
Yeah, I mean, for me, it seems quite similar. For example, the boundary recognition and the usage of the spring, and also considering the displacement at the output positions. So I'm just guessing what would be the major difference, for example, in terms of the optimization formulation or, yeah.
Yeah, I think the main thing is the bistability in the inputs. I mean, these I think are compliant mechanisms. They are creating the type of deformation that we want by elastic distortion. So I think like I don't know how exactly you define a compliant mechanism, but I would say these are. The main thing that we're doing here is it's the digital logic part, which is I think unique, that our inputs snap between these two distinct locations. And so the mechanism has to kind of push hard enough on the output to get it to go into its second well, and the discontinuity and the gradient that problem presents, and trying to satisfy kind of this complex logic. But I mean, I think these are just kind of difficult compliant mechanisms.
Okay, thank you. Just one follow-up question. Just out of curiosity, is the logic is necessary to be binary? I mean, can the output be continuous?
Yeah, I mean, you could design an analog mechanical computing system. That was a decision that was kind of made before I started this work, that we're interested in these binary ones. I can't say with certainty that like you should do binary, or I think that there is ways that you could accomplish different mechanical computing tasks with both digital and analog. We are just kind of picked digital to look at for this project.
Okay, thank you.
So thank you, Deng. So any other question? You can unmute yourself and ask directly from Kenny your question. When we are waiting, Kenny, so you showed the intuitive design that they had a small feature and sharp edges, and you mentioned that. So for sure, that is not mechanically very sound, and it's creating some of the issue, stress concentration, or will cause some of the initiation for damage and crack propagation. But even in the topology optimization, when you have the feature, they are connecting to each other, it is like the joint that we will see in the compliant mechanism that our friend was referring. So do you introducing any manufacturing constraint to consider this kind of the future failure if you have a repetitive, I don't know, these gates that you are using for many times to prevent the damage at those small feature when two feature comes together? It is like a joint.
Yeah, we haven't included any specific damage type constraints yet. What I'm kind of the most recent stuff I've been working on is putting a more explicit minimum feature size control. So right now I'm imposing a length scale through the filter, but as we all know, that doesn't actually guarantee that you avoid small features. It just makes them artificially less stiff. But unfortunately, with compliant mechanisms, sometimes that's advantageous for the performance of the design. So the filter doesn't necessarily get you away from small features. And so I'm looking at a couple different techniques for how to basically put a minimum feature size from a manufacturing point of view, which is kind of a, you know, in a sense, it's a proxy for avoiding damage, because we know if that feature isn't tiny, it's less likely to break right away. I do think that is a next step in this work, is to put, whether that's, you know, reducing the yield stress or a damage model or something like that. I do think we want to look at making sure that these hinges aren't going to break right away. And that really is just kind of motivating for, I think, why optimization is a good tool for this problem, is that we at least we all know that we can look into those types of constraints, whereas the intuitively designed ones, they have to spend a lot of time kind of manually tuning just to get the logic to work. And so they're not, it's not really feasible to keep iterating manually to like reduce, you know, stress constraints and things like that. It's hard enough just to get it to work. Whereas we have the infrastructure in place, at least, to add in these more complex design constraints.
Okay, thank you. We have a new question in the chat from Mohammad Hashemi. So Mohammad asking, thank you for the presentation. Comment on the practicality of such a mechanical computers. How useful are they in practical applications, considering the limited scalability of them?
Yeah, I mean, that's a good question. To be honest, it hasn't been a huge focus of my work here. But I would say that it's, you know, I'm not suggesting that we're going to get rid of our electrical computers anytime soon and replace them with mechanical computers, but there are certain applications where you need to perform a limited set of calculations, and you want to be able to do that in a way that doesn't require electricity. I think you know, it's going to be niche applications for sure. I think the NASA rover is a good example, right? Like, if you just want to do some very small amount of sensing or some logic, and you don't want to have to worry about your electrical system corroding or things like that, it's going to be kind of one-off, very specific applications where this is the right thing to do, hopefully. It's not like you're going to decide to like make one of these with millions of gates and try to reproduce some functionality of modern computers.
Okay, so next question is the potential energy of your bistable elements symmetric or asymmetric?
So right now we are looking at symmetric, since just in the gate design phase. That is a good question, though, because I think when we start combining many of these gates in order to get the propagation, we're going to have to do something with either making the potential not symmetric, so that we have these, like, you can kind of make like a biased well, or make the stiffness, like, you maybe keep them symmetric, but as the gates kind of go downstream, the stiffness is decreased in a way, because you can't just propagate this energy forever, because you're going to have energy that goes into the, you know, the elastic deformations. And so that will be a consideration once we start kind of combining chains of these things.
Okay. Okay. So when we are waiting for a new question in the chat, so when you were mapping from 2D to 3D, are you allowing to your topology optimization change the layout in the third direction? For example, if in the cantilever beam, if you go from 2D to 3D, if you allow the design optimization in the third direction, you know that the design will be changed based on the removing or adding material in the third direction too. What is the case here?
So here the design mesh was 2D, and then that design mesh was mapped onto a 3D analysis mesh, but it was, it was just extruded. So the design had to stay strictly 2D.
So it means it is not actually optimized for the third direction. Yes?
Right. And that mostly came from at the scale that they were manufacturing these, their printing technique is 2D. And so the design has to be 2D so they can be built, but we want to look at how, and it's still going to perform in real life. So we want to look at the 3D performance, but we know that the design has to be 2D.
Okay, because of the manufacturing, it is 2D. Okay, it makes sense. So, and you saw that one of the issue was when you try to make it, it was buckling. If you add the buckling constraint or buckling analysis in your topology optimization, probably you can predict or do such a way the design to reduce the buckle in the third direction or any other direction. Yes, so at this point you don't have the buckling in your analysis. Yes, into topology optimization.
Right, and my mentality there is that it's not the buckling that we care about. It's the fact that when it buckles, it doesn't hit the performance goals. And so rather than put in a constraint to avoid buckling, what we really mean is like we just want it to work. And so we just needed to put we just had to make the model more relevant in the optimization so that the optimizer could drive us to a design that satisfied the logic, which kind of implicitly meant it didn't buckle in that third direction.
Okay. Any other question from the general audience? No question? Okay, I will go with one more. So, Kenny, when you started to 3D printing this and you saw the issue, it was any issue in the manufacturing of this? Did you have any feature that you guys cannot manufacture based on your topology optimization and smooth or change your design to be manufacturable?
So I would say that we haven't actually gotten to the printing phase. We are hopefully that is in a matter of kind of weeks at this point.
Okay.
Mostly it was taking we got these 2D results and we were really excited about them. And then when we went to think about, well, let's try to build one of these, we were trying to make the model more and more realistic to take
Okay, I got it. This was similar.
And then I think we learned a good lesson though, that if we had just taken our 2D design and hoped that it worked, we would have printed something that had no chance of really behaving how we wanted in real life. And so going down that route of investigating these things taught us a lot about the gates. In speaking with the manufacturing engineers, it's mostly been just about feature size. Their 3D printers, it sounds like, are pretty good and able to handle these complex shapes. It's mostly just making sure that, when we take the topology optimized design and interpret those small hinges, making sure that those have adequate feature size is the main. That's the we're looking at right now.
You talk in some point about this self-contact. If I missed that, so how you implemented the self-contact in the model?
So there is no self-contact in the model.
At this point, it is not.
Right, and so that's why, when I did some very preliminary shape optimization here, and you can see that the design starts to intersect with itself because we don't. So that the model doesn't see that this material is intersecting. And so there's a couple ways you can handle that, right? You can just avoid the contact. And so you could write constraints that make sure that the design doesn't hit itself just, by looking at the geometry. Or you could model it. I think we would like to eventually model it. But differentiable contact is a hard thing. And we're not quite at that, being able to put that in the optimization today. And so in the absence of being able to model it and differentiate it and understand how to, because that's going to bring in a huge non-smoothness to our problem, right? When that design goes in and out of contact, you're going to have a big jump in your response. And so in the meantime, we would just like, I think, to avoid the self-contact. And so we know how to do that. We just haven't put those constraints into this workflow yet.
Okay. Thank you very much. And let's thanks Dr. Swartz. I really appreciate it. It was very interesting.